Good morning. We've been talking about designing digital filters. Today I want to do a complete filter design. And I call this the complete filter design because we're taking in all aspects that's in a typical filtering problem. Not only are we going to talk about designing HFZ, but this is going to be a complete system including the sampling. Analog to digital and digital to analog conversion. Now, usually when we have a problem like this, let's say you recorded someone speaking and you want to filter out some noise in the system. You have to take into account the sampling frequency, you have to take into account what frequencies you want to keep, what frequencies you want to attenuate, that type of thing. So let's start and let's look at this example. Let's say we're going to design a Butterworth filter, low-pass filter. The analog signal is band limited to 5 kilohertz. And it says the filter must not amplify the signal, have no more than 2 dB of attenuation in the pass band, which is going to be from 0 to 1.5 kilohertz, and at least 15 dB attenuation in the stop band, which is from 3 kilohertz on. Now, let's take these specifications, which is the way they're usually talked about, and write them out, make a graph. First thing we need to do, is select the sampling frequency if it hasn't been already. So, we want no amplification of the signal, so it's not going to go over 0 dB. We want no more than 2 dB of attenuation. So in the pass band, which is from 0 to 1.5 kilohertz, in other words from 0 to 3000 pi radians per second, we want the amplitude to be between 0 and minus 2 dB. The stop band is from 3000 hertz on, so 6000 pi radians per second, and we want at least 15 dB attenuation. So this would be the graph of the filter that we want, the performance that we want from the system. First we need to translate these specifications into specifications for H of Z. Now we need to choose a sampling frequency, if I had said before, if it's not given. We know that the signal is band limited to 5 kilohertz. We know that if we want to avoid aliasing, the sampling frequency has to be more than twice the highest frequency in the signal. So we want at least 10 kilohertz for the sampling frequency. And we can just choose 10 kilohertz for simplicity. Now, we need to change these specifications into the specifications for H of Z. Now, this is not, and the reason I want to do this example is to go through this process. We don't use, well, obviously we don't use the bilinear transformation here. This is a relationship between xa of t and x of n in our system. It's the relationship between this, the specifications here, and the specifications here. So that would be passing through our sample system. And we know that the relationship between the frequencies when we have sampling is this. And this is not the same t, of course, as the bilinear transformation. This is the sampling period, 1 over f of s. So we know that little omega is big omega over f of s. And so we can get the pass and the stop frequency for our digital filter if we know the sampling frequency. And so these would be the specifications for H of Z. Now, this is a linear transformation, This frequency is double this frequency. 6000 pi is twice 3000 pi. Since sampling is a linear operation, here we have 0.6 pi and 0.3 pi, something we didn't have when we did the bilinear transformation, which is not a linear transform. So these are the specifications for H of Z. Now, if we're going to design an analog filter and then transform it into a digital filter, we need to pre-warp the frequencies. So let's pre-warp to get the specifications for HA of S. Let's say for simplicity that t is going to be equal to 1. And so we substitute omega p, omega s, and we get 0.5 and basically 1.3 or 1.4 for our frequencies. And so we needed to design a filter for these specifications. The first thing we always do is change from dB to non-dB. And so 0 dB is 1, minus 2 would be minus basically 0.8, and minus 15 is basically 0.1778. And so we use this, right, where we can read off our k over square root of 1 plus epsilon, and k over a, to get k epsilon squared and a from these amplitudes. And then we choose our n. We go to the formula for n, we see that this just makes it under 2, and so we can choose a filter of order 2 to meet the specifications. Anything less than order 2, we won't meet specifications. We then find our omega c, we substitute, and we see that omega c has to be between 0.5826 and 0.5849. So I could choose the simpler the number, the better. Here I choose 0.583, right? 0.583, 0.584 would have been fine. We know where the poles are. We've done this before. We've found where the poles are for filters of order 2. But again, right, in this case, this pole has an angle of under 35. The pole on the bottom has an angle of 225. And so this is going to be our pole locations. And when we multiply this out, this is what we're going to get. Now we have to scale by omega c because omega c is not equal to 1. And this is what we get, right? Substituting, doing all the multiplications, this is what we get for our final answer for HA of S. So this would be our Butterworth analog filter. Now we need to transform it into the digital filter that meets the specifications for H of Z. And so we do this transformation. We substitute S using the bilinear transformation. Since t is equal to 2, it's just this transform here. And so we substitute in for S. Now we see this is going to make it long. This, even for a filter of order 2, right, it's going to be a few multiplications and additions. It's not terribly hard, but it's long, it's kind of tedious, so take care when you're doing this. So we multiply by z plus 1 squared. I multiply by z plus 1 squared simply to eliminate the denominators. And once we have that, we do all the multiplications. So then we finish all our multiplications. We add all the terms together, all the z squared, the z terms, and the z to the 0 terms. And then this could be our final answer, except that generally we normalize this. We want this first term to have an amplitude equal to 1. So let's divide everything by 1.821, and we would get this here. Or if we multiply it out, we'd get this term here. We could leave it like this, although in most cases our filters are written in terms of negative terms of z. So we could multiply numerator and denominator by z to the minus 2 and get this here. But either one of these, since we're really, the part that we're really looking at are the coefficients. And so this would be our filter, the final design of our filter. In this h of z, if we put this h of z into our original system up here, it will meet these specifications. Now I want you to go through this again. I want you to do this. Repeat it for this case. So we have a different system, different passband, different stopband. Go through all the steps just as we just did, and find what h of z is. Repeat problem 1, changing the specifications, right? Changing the passband, the stopband, the magnitudes, and the sampling frequency. So you're going to design 2 filters in this case.